Right, so let's start the second session this morning. So my name is Seung-Gyu Min, the chair of the session. The next speaker, the first speaker of this session is Professor Daniel Crawford, and he's going to talk about the reduced scaling coupled cluster theory in the frequency and time domains. So let's welcome Professor Crawford.
There we are. All right, can you hear me clearly? Good. Good. Accept. Okay, now I can. Good. All right, sorry for the technical problems to begin with. First of all, I'd like to thank the organizers very much for their kind invitation. I have been through the airport in Incheon multiple times, going to destinations outside of Korea, and therefore I don't count myself as having visited Korea until, any place until you leave the airport, you haven't been there, right? So at least now I can say I've been to Korea, and I'm very glad about that. So thank you. So I'm going to tell you a bit about work that we've been doing fairly recently in my group, focused on couple cluster theory. So I thank Piotr for giving a very nice introduction to the domain itself, and I will be able to skip a lot of the details of that in favor of his presentation. But we've been doing a great deal of work on what are known as response properties, so spectroscopic response properties in particular, and we're very interested in lowering the cost of these calculations, that is the computational demands of these calculations, using two different domains, frequency and time domains, as you'll see. But first, I'd like to give just a little bit of information for those of you who are interested in the Molecular Sciences Software Institute. This is another project that I have been closely involved with for the last almost 6.5 years. It's hard to believe. This is the Molecular Sciences Software Institute. We launched it to try to enhance the software development efforts of the computational molecular sciences community, broadly defined: quantum chemistry, biomolecular simulation, materials, and so on. And this was funded by the National Science Foundation in the U.S. Initially for 5 years, and we've been renewed for another 5 years. And so we hope that we're having an impact. Some of the things that we've done: we have a team of software engineers. We call them software scientists at what we call the MOLSI, for the Molecular Sciences Software Institute. Our headquarters are at Virginia Tech, where I am from. And right now we have 9 software scientists on board, and they really do span the whole domain of computational molecular science, as well as computer science and applied mathematics. We host and help organize software-focused but community-driven workshops. We've had about 25 of these so far, and about 850 participants have been involved in those. They slowed down during the pandemic, as did everything during the pandemic, but they're starting to pick up speed again, and we're going to have a fairly large one coming up in the spring in the machine learning domain. We also have a number of cyber infrastructure projects, software development projects that are designed really to help the broad spectrum of community codes. We have our basis set exchange is of particular interest to the quantum chemistry community. This is something that we took over and re-envisioned from Pacific Northwest National Labs. And that website, actually, the basis set exchange, gets about 10,000 unique visitors per month. and it's having a wonderful impact. We've significantly enhanced the capabilities of the basis set exchange. We also have our QC archive. We have the COVID-19 molecular structure and therapeutics hub, the MolC driver interface, and so on. These are heavily driven by interoperability. So really trying to help as many codes at once to interact through data and capabilities both. For example, our QC archive public database, it's got about 113 million computational results in it, and that's publicly facing. And so there are a number of groups that are using that for machine learning applications, for example, building new force fields among them. We also have a very, active education initiative. We've had about 2,000 students who've gone through some of our summer schools or other educational workshops. That's face-to-face instruction. And then we have about another 5,000 students per month go through online self-guided instruction as well. We have a software fellowship program, so we support postdocs and graduate students all over the United States. We've supported about 105 students and postdocs so far over the lifetime of the program. And we've had that group, as well as our board of directors and so on, have published quite a few papers focused on the software domain, about 115 so far. We have an Institute H-index for whatever that is worth to you that you can see. Anyway, that's the update about the MolC. If you're interested in that, I'm happy to talk about it. It's a fairly large effort, and it's very important to me, but it is separate from my research group. I maintain it separate from my research group because the MolC is there to serve the community, not my research group in particular. So I have to keep these apart from each other. And my group is especially interested in various forms of spectroscopy, particularly spectroscopy of chiral compounds, and especially linear chiroptical spectroscopy, as it's referred to, whether it's in absorption or refraction, scattering, or even emission. We work on methodology and software implementations of this new methodology for what we hope will be very high accuracy simulations of these kinds of spectra, particularly these spectra in solution, which makes it an even more challenging problem. So the central to these is the Rosenfeld optical activity tensor, as it's often referred to. When we tell students about induced dipole moments, so when we're teaching this in undergraduate physical chemistry or in general chemistry, we always tell them about how dipole moments can be induced in molecules by external electric fields. What we don't tell them about are lots of other terms that can also induce dipole moments. And if you have a chiral compound and appropriate polarized fields, then you have additional terms that look like polarizabilities, but instead of multiplying the electric field alone, they multiply the time derivative of the magnetic field. And that particular tensor, as we refer to it, this G prime tensor, is the Rosenfeld tensor. It is a central quantity to all of these chiroptical spectra. It's certainly not the only quantity, but it's a key term that you must get right. And it depends on both the electric dipole moment and the magnetic dipole moment. So in this particular form, as you see here, we have a sum over all of the excited states of the molecule with electric dipole and magnetic dipole transition moments from the ground state to these different excited states. And the denominator, you have energy differences corresponding to excitation energies and the external field energy. The trace of this tensor is related to optical rotation, so optical rotatory dispersion. And the residues of this tensor are related to the rotatory strengths that you would measure in a circular dichroism experiment. And so whether it's electronic circular dichroism, so that the energy levels you're talking about are electronic excitations, versus vibrational circular dichroism, where the transitions are in the infrared, this is still the central quantity that you have to deal with. But it's not the only quantity that you have to deal with. And unlike
Yeah.
Now you can hear me?
Yeah. I can hear
All
you.
right, we're back. Okay, so as I was saying, we have a number of different types of tensors that we need for calculating these various types of chiroptical spectra. The top one, again, is just the Rosenfeld optical activity tensor. The one in the middle is the electric dipole, electric quadrupole polarizability tensor. And one at the bottom is the sort of standard dipole-dipole polarizability tensor. However, we do not evaluate the sum over states expansion that you see in these expressions because it's highly computationally inefficient to do that because we'd have to calculate all of the excited states of these molecules, and that's naturally very complicated to do. So instead, we adopt the response theory framework, which is simply a form of time-dependent perturbation theory in which instead of the zeroth order wave functions you used being eigenstates of the zeroth order Hamiltonian, it's simply, in the case of coupled cluster theory, the determinantal basis, much more convenient to work with. And that leads to coupled cluster linear response functions, which are key to this. We have a general code for dealing with these linear response functions in which you can plug in whatever types of operators you want. In the case of the optical activity tensor, electric and magnetic dipoles, for example. And the key step to this really is that you have to solve, instead of a large-scale diagonalization problem, you have to instead solve systems of linear equations for each of the external field operators that you need. And that's a much simpler task computationally. It's not trivial, but it's certainly much simpler than having to calculate all of the eigenvectors of a very large Hamiltonian matrix. And so we do all of this work within the Sci4 package, which is a fully open source package. Our main development is done fully open source. And if you're not familiar with it, please feel free to take a look. We welcome pull requests from the larger community. We have the number of contributors to the package has been growing dramatically, which makes me very happy. So some of the recent developments out of my group in this area, working on explicit solvation. A lot of that work has been done by Rui da Cunha, who got her degree with me last year and is now with Laura Gagliardi doing a postdoc at the University of Chicago. She also worked on local pair natural orbitals that I'll say a little something about dealing with response properties. Monika Kudrycka, who's now at Zapata Computing, worked on quadratic response functions. Dr. Kirk Pierce was working on atomic axial tensors, a subject that I would very much like to talk to Roger Amos about, since he did a lot of the pioneering work on that I found very helpful. And then more recently, some work in real-time coupled cluster, so explicitly time-dependent coupled cluster that we've dived into. So explicit solvation, we've found that implicit solvent models are extremely ineffective in reproducing chiroptical properties. You get it right sometimes, but they're not reliable. And the reasons for this deal with a great deal with the fact that optical activity, and I'll just use optical rotation as a specific example of this, you can't think of this as a property of the solute molecule being perturbed by the solvent. You really have to think of this as a property and the explicit solvent molecules in the local environment. What does local environment mean? That's one of the challenges, is identifying exactly how much explicit solvation has to be maintained. And that was part of Ruhi's work, using molecular dynamics trajectories involving explicit solvent molecules and seeing how large of a sphere of solvent molecules we had to maintain and how well the property converges with the number of snapshots that you take out of an MD trajectory. And it works well for some solvents and some molecules, and it's more problematic for others. For the size of the system, we were forced to use density functional theory for this, and the results are highly dependent on the choice of functional, not necessarily a surprise. But you can see, for example, this is for methyloxarane surrounded by explicit water molecules, where as we just take the solute alone, we're quite a distance away from experiment. But with explicit solvation surrounded by, say, 10 to 12 water molecules, we move significantly closer to the experiment. I still don't think it's good enough, but it's a lot better. However, when you consider the same system in methanol, there's a sign change in methanol relative to water that we cannot yet reproduce. And so a great deal more work is needed there. And some of that is related to deficiencies in the density functional choices. So we'd like to go larger, and we'd like to be able to do couple cluster on these, and that's part of the motivation of this work. So a great deal of work on local pair natural orbitals that Ruhi led, that we're very proud of. If you use, I'm going to avoid going into some of the details of the local paranatural orbital simply in the interest of time, but the idea, this idea that has been resurrected by Frank Neza and coworkers is doing so extremely well for energetics and a number of other properties. It's not effective when applied to these kinds of response properties, polarizabilities, optical rotation, and the like. And part of that is because these properties depend heavily on very diffuse regions of the density and how it responds to the external fields. But it's those diffuse regions of the density that you describe the worst with local paranatural orbitals in the first place. And so we've worked to extend this to building new types of expansions for the virtual spaces, still based on paranatural orbitals, but instead using perturbation-aware density. So they're in fact first-order derivatives of the density with respect to external fields. And the idea is simply to get improved choices of the virtual space so that you can still use exactly the same kind of LPNO framework that has been so successful for ground state energetics, for example. And if you look at this this is still a small system because we don't have a production level implementation, we just have simulations. This is a helical chain of H2 molecules. This is for the polarizability, and this is for the specific rotation, so the optical rotation. As a function of how tightly you choose your cutoffs for the LPNO definition. And what you see is that standard PNOs are doing quite poorly relative to the canonical result, which is the black line at the top. But these PNO++ type methods, this perturbation-aware type method, converges very rapidly to that without significant cost increases. It's a little bit more difficult for optical rotations. Optical rotations are harder because of the mixed electric and magnetic properties, but it's still an improvement over the original PNO, which is simply erratic. And we've tested this for larger systems. But more recently, we've been thinking about, is reduced scaling more let's say, optimum rather in the time domain rather than the frequency domain? And the reason we thought about this in the first place was because a long time ago, I recognized that the sparsity of the ground state couple cluster wave function is reduced when you go from the original wave function to the derivative of the wave function, that is the first order perturbed wave function with respect to a field. And in this plot, the blue here is the original unperturbed couple cluster wave function, the distribution of the amplitudes with respect to their magnitudes. And so you'll see that I have fairly large, these are negative numbers, so around 10 to the minus 5 or so is where I see the most number of my T amplitudes, my cluster amplitudes. However, if I do the same plot for an electric field perturbed couple cluster wave function, I see a shift in the distribution about 1 order of magnitude up. And so that means that I've lost a great deal of sparsity, which means I'm going to have to do more work because I have to keep more of the wave function around in order to achieve the same results. However, if instead I explicitly turn on a time-dependent electric field and allow this to propagate in time, you get the green curve, which is hard to distinguish from the blue. The sparsity distribution hasn't really changed very much. So that led us to wonder, what if we carry out these kinds of calculations explicitly in the time domain and extract the properties we want from those trajectories, as we could call them? Okay, so this moves us into real-time couple cluster, where we're simply taking the time-dependent Schrodinger equation and using the couple cluster wave function to parameterize our time-dependent wave functions. And so you have the right-hand form of the wave function, which I've realized I put on the left-hand side of the screen, I'm sorry. And then I have the left-hand form of the wave function, which I put on the right-hand side of the screen, so forgive me for that. But still, these are what are referred to as phase-isolated forms of the wave function, and that's what the e to the I epsilon is, epsilon being a real time-dependent function. When we bring these back into the Schrodinger equation, we can obtain equations explicitly for the phase exponential, which is the quasi-energy as it's called, and then explicit equations for the T component amplitudes that parameterize the exponential, and these lambda amplitudes, which parameterize the left-hand wave function, which are just Lagrange multipliers. Those are what we need. We need the time dependence of the T and lambda amplitudes to get a time-dependent density, which we can then use to calculate time-dependent one-electron properties, such as electric and magnetic dipole moments. Common algorithms for propagating these wave functions, because these are very straightforward in many ways, very straightforward, fourth order Rungo-Kutta, and similar types. And we've coded up about 18 different integrators just to test them to see how they do with couple cluster structures. So you can get absorption spectra from these, right? For example, if you calculate the time-dependent dipole moments, so this is the alpha Cartesian component of the dipole moment as a function of time, using the couple cluster wave function left and right, this is related to a certain term in the expansion to the polarizability and the electric field, the product of the two. You can take the Fourier transform of this, of the polarizability, to get the dipole strength function, and the imaginary component of that is the absorption component that you want, so that you can compare directly to, say, equation of motion couple cluster or even experiments. So you can see the orange here, the black lines here are stick spectra that you would get from equation of motion couple cluster, and the orange here, that's the imaginary part of the Fourier transform of the polarizability. So you can see that they line up as we expect them to. And this is just for a small chiral molecule, hydrogen peroxide, and using a form of the electric field that is just a Dirac delta pulse, so a broadband field. You can also do circular dichroism spectra with this, because through the magnetic dipole moment, you can calculate that as a function of time. That is related to the Rosenfeld tensor multiplied by the time derivative of the electric field in this case. And if you take the real part of the trace of that resulting magnetic dipole, or I should say the result of the trace of the Rosenfeld tensor, which is pure imaginary, then you can get the circular dichroism spectrum. And one of my students put together this very nice animation showing how long you have to propagate the wave function here in order to see convergence of the spectrum for direct comparison to EOM. I should say, these are not cheap calculations. Okay? I would love it if they were, but the fact is that you have to take a lot of time steps. So we would need a great reduction in scaling to make this practical, but it's still a fascinating piece of ground to try to explore. What you also see is that some of the transitions can be very difficult to get the rotatory strengths to match with the converged results in the end, but you can do it. So we examined several different techniques for trying to speed up these calculations. For example, we wanted to see what would happen if we did this with just single precision arithmetic. There have been quite a few folks in the field who've examined couple cluster in particular, using single precision arithmetic to see if you really need double precision, which is sort of standard for all of us in our computer codes. And for a lot of other properties, you don't need it. This is one of them. We found that we can exactly reproduce absorption and circular dichroism spectra, just carrying out the entire propagation using single precision arithmetic. Now, if you needed, for example, very high precision, if you were going to calculate numerical derivatives using these things to extract individual response components like polarizabilities directly, then it may be problematic. You may not be able to get away with single precision, but for certainly reproducing absorption spectra or circular dichroism spectra, double precision is not needed. So that gets you roughly a factor of 2 improvement, so that's welcome. We also worked with a GPU version of our code to see what kind of improvement we could get from this. And what we see is for small water clusters, we start to see comparison between a GPU in double precision versus a CPU in double precision. We can get a little bit better than a factor of 14 speed up in those calculations. And this is not a sophisticated GPU implementation. This is a very straightforward, I mean, we could optimize this, but at least to begin with, I was very happy with a factor of 14 to start with. At least I'm very optimistic about it. You can also decompose the density as a function of time and identify what are the key components of individual peaks. So you can identify key transitions. One of the criticisms of real-time type methods or time-dependent type methods is that it's hard to extract information about the individual excited states. But I think with the individual density components, you can do this because we can make direct comparisons. And this is kind of hard to see in this plot, but these are individual orbital pair contributions, occupied and virtual orbital pair contributions to the time-dependent density. And we can see how these compare to the reference, the complete spectrum. So we can extract the individual orbital contributions to every individual peak. And it matches up beautifully with EOM, for example. So that would be very useful, say, for core excitation spectra and identifying exactly what types of peaks you're seeing in very high energies. So reduced scaling in the real time, does this work? Well, we're still working on that. what we see so far is that absorbance spectra, for example, we've tried several different reduced scaling techniques. There's the projected atomic orbitals by Polai and Szabo. There's the P&O type work from Neza and co-workers, and then the P&O++. What we can say is that you get a greater reduction in the size of the wave function, in the virtual space, I should say, with the P&O++, without as dramatic a shift as you see, for example, with the projected atomic orbitals, the PAOs. You get extra shoulders and things like that from this, because the fluctuations, I guess is the right term to use, in the wave function in the presence of the field is greatly impacted. It's highly sensitive to the nature of these cutoffs and how you truncate the space. For CDE spectra, it is unsurprisingly even more sensitive. That's what we find for all of these chiroptical properties. They're extremely sensitive to the level of theory. And so I can't say that we have succeeded at all yet, but we're making progress in this and learning a great deal about it as we move forward. So I'll just quickly wrap up. We're very pleased with the LPNO++, that is these perturbation-aware densities, to try to reduce the scaling of couple cluster response theory without loss of accuracy. In our collaboration with Thomas Peterson in Oslo, we've implemented these real-time couple cluster methods and found that single precision techniques and GPU techniques can help a great deal with those. We have a great deal of work to do in the reduced scaling real-time couple cluster, but we've really only just gotten started with this. And so we're working on a lot of different virtual space definitions and truncations to see what works and what doesn't. So with that, I will thank the folks who paid the bills, and I'll especially thank the students and postdocs who worked on this directly. They're really outstanding folks. I'm very pleased with my group right now, and I'd be happy to answer any questions if you have them. Thank you.
All right, so now it's time to questions. Okay, Michael.
All right. Thank you very much for a very nice talk. I really like that real-time method. Sorry, I see very strong echo.
You can remove your.
Can you?
All right.
Remove your.
Robert.
Yeah, take it
All
off.
right. The approach you described is good for computing static spectra.
Yes.
And,
Yes.
Any thoughts about time-dependent spectra, time resolved?
So if you're thinking about, say, dynamical spectra so if I have by static spectra, right, I have a fixed Born-Oppenheimer structure, and I'm simply keeping that fixed as I calculate the spectrum. You could add a whole another layer to this. Thomas Peterson and his folks in Oslo have been making some progress, and there are other techniques for doing this. We haven't touched those yet. We're just using static nuclei. But as soon as you layer on the nuclear dynamics that you would need for dealing with, conformational flexibility and the sort, the level of complexity of the calculation increases dramatically. So we haven't touched it yet. I'm not saying we won't, but we're not there yet.
So is it not like you may take a snapshot from trajectory, assume that the molecule exists in this geometry for?
No, we can do that, right? We can take a fixed structure. So we can take a molecular dynamics trajectory, take a fixed structure with solvent around it, and do that calculation and then average that spectrum over the trajectory. That we can do.
But the spectrum will be enormously broad.
Yes. Yes. Well, it depends. Not necessarily. I mean, it depends on how dramatically the structure is changing. If I have large numbers of conformation, or if I have significant changes in the electronic structure of the solute, then yes, I'm going to see significant broadening. But if the fundamental electronic structure is not varying dramatically, I won't see huge changes in the spectrum, even averaging over lots and lots of trajectories. In fact, I might consider that average to be closer to the physical result that I want in that case. As long as the electronic structure of the solute itself in particular is not varying dramatically, and my methods therefore are qualified to describe them, which couple clusters should be, I wouldn't necessarily expect huge broadening in the spectrum. Certainly not beyond what I would expect physically. Mhm. Sure.
Okay, thank you. And any other question? All right, Wika.
So this is a bit of a cheeky question because I've been watching too many machine learning talks, but you've gone double precision, single precision GPUs. Have you thought about half precision, or is that just asking too much of your maths?
I haven't tried half precision, and so I'll explain. Part of the reason we just went from, we did try mixed precision, right? So some components in double precision, some in single, but you're talking even, half precision, reducing it further. We did all of this by simply adjusting types in a Python base code, which made it trivial to test pure single precision versus pure double precision. If our Python library allows that, and I have never checked to see if it does, then I could trivially try that, but I just have to see, and I honestly don't know. It would be fun, and I could try it straightforwardly.
It's just that NVIDIA has just produced all these, half precision chips for the machine learning stuff.
True.
So you never know.
That's true. Yeah. Well. Yeah. I would not read too much into the widths of those peaks. Okay. The reason being that the widths of those are really related to how long we propagate. If we keep propagating and propagating, they're basically going to converge to stick spectra. Okay, because there is no physical process in our simulations that allow decay of excited states back down to the ground state. So we have infinite lifetimes implicit. And so the only reason that we get any width there is simply because the trajectory hasn't been run long enough. Yeah. But they look really nice. Yeah.
All right, any other question? Okay, if not, then let's thank Professor Daniel Crawford again.
Thank you.
And actually, we